YOLO has ruled real-time detection for years, but the transformer revolution just shattered its records. Today, we're exploring how RF-DETR-Seg brings pixel-perfect masks to real-time vision, dethroning the legacy models.
For the longest time, real-time vision systems really only ask two things. What is it, and roughly where is it? But, what if a bounding box just isn't enough? I mean, a simple rectangular box gives you the general area, sure, but it completely fails to capture the exact contour of, say, a surgical tool in an operating room, or a pedestrian navigating heavy traffic, or even a tiny defect on a fast-moving manufacturing line. When the stakes are high, you absolutely need more than just a box.
And this brilliantly illustrates the crucial leap from basic localization to true pixel-level spatial reasoning. A traditional bounding box just highlights a general zone. But an instance mask, that's where the magic happens. Instead of just a box, the model generates a separate, hyper-precise mask for every single detected object. It allows the system to actually reason about shape, overlap, and really fine spatial details.
Okay, let's dive into this. We'll be looking at 1. Beyond the bounding box. 2. Inside the RF-DETR architecture. 3. Breaking performance barriers. 4. Real-time video segmentation. 5. Mastering complex real-world scenes. And finally, 6. The future of vision.
Real quick before we really get under the hood, just a reminder for the developers tuning in, the full article and all the Python code used for this exact demo are available right now. Just check the description or the pinned comment to grab the code and try it out for yourself.
Section 1. Beyond the bounding box.
So why are industries actively demanding this shift to instance masks? Well, in high-stakes fields like robotics, autonomous driving, industrial inspection, medical imaging, and retail analytics, overlapping objects and precise boundaries literally dictate downstream decisions. A bounding box might tell a robotic arm a part is somewhere in a bin, but a mask tells it exactly how to grip it. A box tells a self-driving car a pedestrian is there, but a mask shows exactly where their limbs are and how they're moving. Bounding boxes are simply becoming inadequate for the precision these industries demand.
Section 2. Inside the RF-DETR architecture. Let's open the hood and explore the components that make this architecture so powerful. The first one is the Dino V2 backbone. This is a massive departure from traditional YOLO models, which rely on convolutional neural networks. Dino V2 is a robust vision transformer that basically acts as the model's eyes. Because it's been pre-trained on massive datasets, it extracts incredibly rich visual features. This means it can easily understand completely novel domains right out of the gate. Whether you're feeding it aerial imagery or highly specialized medical scans, it adapts beautifully.
Next up is the deformable attention decoder. Think of it like this. Imagine walking into a messy room. You don't stare at every single square inch of the wallpaper equally, right? No, you instantly focus your attention on the important stuff, the TV, the couch, the dog. That is exactly what deformable attention does. Instead of evaluating every pixel equally, it focuses its computing power only on a small number of important image locations. This keeps the vital context intact, but makes the model dramatically faster.
And here is where things get really fast. Because of this architecture, RF-DETR predicts objects directly. This means it completely eliminates the non-maximum suppression, or NMS, bottleneck. Normally, NMS is required to filter out duplicate bounding boxes, so dumping it entirely drastically reduces post-processing latency. Honestly, this single advantage is what makes this architecture an absolute powerhouse for real-time video streams.
This explainer is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. As founder Satya Malik notes, they take projects through the full journey, not just the easy parts. You can reach them at contact@bigvision.ai.
Section 3. Breaking performance barriers.
Now that we know how it works, let's look at the hard proof of how it utterly dominates the benchmarks. What's really interesting here is that blistering 2.3 millisecond latency on the Nano model. For strict real-time edge applications, where power and compute are incredibly constrained, you're getting inferences in just 2.3 milliseconds. But if you have the compute power, scaling up is just as impressive.
And that brings us to this number, 60.1. Take a moment to let that sink in. This is a historic milestone in computer vision. The RF-DETR 2x large model finally broke the 60 AP barrier, specifically scoring a 60.1 on the AP 50 to 95 metric for real-time detectors. It proves that you absolutely no longer have to sacrifice accuracy for real-time speed. Looking at the instant segmentation benchmarks, the story is just as wild. RF-DETR-Seg scales beautifully across its model sizes. The Nano hits 63.0 AP50 at just 3.4 milliseconds, while the 2X Large pushes all the way up to 73.1. By doing this, it completely dethrones YOLO V8, YOLO 11, and even YOLO 26, claiming the undisputed top spot for real-time instant segmentation.
Section 4. Real-time video segmentation. For the AI developers out there, the brilliant part is how incredibly simple it is to implement this powerhouse into your own dynamic video streams. It's just 3 steps. First, install the package using a simple pip install RF-DETR. Second, load your desired model size. And third, pass your image or video frames directly to the predict method. That is literally the whole shebang. What's even better is that you don't need any special plus extensions for the large segmentation models, and the outputs integrate perfectly with the supervision library for effortless mask rendering.
Section 5. Mastering complex real-world scenes.
Let's look at how these metrics translate into actual visual magic when we throw the hardest possible scenarios at it. One of the biggest challenges in computer vision is dynamic, non-rigid motion. Imagine running horses with rapidly moving legs or overlapping fluffy dogs wrestling on the grass. Traditional models completely lose their minds trying to segment those fuzzy boundaries. But RF-DETR has this uncanny ability to maintain distinct, tight instance masks on erratic animals without flickering or dropping frames. It's a classic nightmare for older models, but is handled with ease here.
The model also absolutely shines in dense clutter and occlusion. Picture a busy street. You've got pedestrians, vehicles, and bicycles constantly overlapping and moving across different depth planes. Thanks to that Dino V2 backbone we talked about earlier, the model handles this severe occlusion gracefully. It perfectly isolates individual instances without losing track of those smaller, partially hidden subjects in the background.
Now, to be completely objective, let's look at the trade-offs. While it flawlessly handles things like high-speed basketball footage, tracking fast-moving players through complex interactions, its high contextual sensitivity can occasionally trigger false positives. For example, it might misclassify a flat training marker on a field as a sports ball. It's a small issue, easily addressed with a little targeted fine-tuning for your specific environment, but it's definitely important to be aware of.
Section 6. The future of vision. So what does this all mean? We are witnessing a fundamental shift right now. Hybrid architectures like this are writing the next chapter of computer vision history. We're seeing the immense power of transformers finally converging with the strict latency demands of real-time vision. It opens up possibilities that were simply science fiction just a few years ago. So the provocative question I want to leave you with today is this. As these tools become incredibly fast and incredibly precise, what will you build with pixel-perfect AI?
Thank you so much for joining me today to explore this explainer on the cutting edge of real-time instant segmentation. I really hope this sparks some ideas for your next big project. If you found this helpful, please hit that subscribe button for more deep dives just like this one. Get out there, grab the code, and start building. See you next time.